So, the dust-dominated era of the universe's history is an exciting and interesting place, and we learned a lot, I hope, by investigating what happened there. What's left to us, we've talked about the future, what's left to us is to press into the past and see what we can say about the early universe. It will turn out that it's difficult to discuss the early universe with the tools that we have, for reasons that I consider quite exciting. As we go deeper into the past of the universe, temperatures and densities rise. It turns out that temperatures and densities rising means that more and more of the species of particles in the universe become relativistic, and basically we are investigating the structure of the universe at higher and higher energies. Higher and higher energies in the context of a quantum mechanical treatment of the universe is equivalent to shorter and shorter distances. Remember, the wavelength, for example, of a photon is inversely proportional to its energy. So to understand the structure of the oldest things, and in some sense the largest, the most distant things in the universe, reduces or brings us to an investigation of the smallest, the structure of the universe at its smallest and most fundamental scale. This is not a class in particle physics, so we will go rather briefly through what we have to say, and perhaps I will post an optional clip where I fill in some of the details. So, onwards to the radiation era. What do we know about the radiation era? This is the first 55,000 years after the Big Bang. The universe is radiation dominated, which means that the scale factor evolves as the square root of T. The value of the scale factor at the transition, remember, is determined from the ratio of the radiation energy density to the dust energy density, because one scales like a to the minus 3 and one like a to the minus 4. This tells us that at the time of the transition, at 55,000 years of age, distances in the universe were about 1.6 ten-thousandths of their current value. To give you a scale, the current visible universe, with its radius of maybe 45 billion light years, was about 7 million light years in radius. So everything that we know, or that we can see all the way out to last scattering, was contracted to a sphere of a smaller radius, and as usual, beyond that was probably more of the same. The temperature increases as the inverse scale factor, so the temperature is related to time by temperature goes like time to the minus 1/2. This is just from the redshift of the photons, as we know. However, there's this funny factor G star up front, and remember, this is extension of the factor G that we mentioned for photons. Remember that the energy density for photons were proportional to G times T to the fourth, and this is that same G. It's 2 for photons. Remember, that represented the two polarization states of a photon. As we go deeper and deeper into the past and the temperatures rise, we basically measure energy not in Kelvin, which is what this conversion has done, but we typically measure kBT, which is the thermal energy of particles, and to relate this to the masses and the units that we usually measure mass in, we measure this in millions or billions, as the case may be, of electron volts. So I will usually refer to temperatures by referring to the energy. When I remember, I will convert back to Kelvin. Now, not much structure formation takes place. So whenever as you move into the past, new particle species become relativistic, the value of G increases going into the past, decreases coming into the future. Note that as time evolves, every time, and the temperature decreases, every time G jumps down, the temperature, since it jumps down rather rapidly, the temperature increases. We'll see an example of that momentarily, and we'll explain how that happens. Now, not much structure evolution happens during the radiation-dominated era. The square root of T expansion of the universe is too rapid for much to be collapsing. So the fluctuations that we discovered at the end of the radiation era were probably present early in the radiation era. And we'll have to understand, in that sense, they were truly primordial, and understanding them is a problem we will defer to the future. Problem number 1. Problem number 2 comes from consideration that I said the visible universe was reduced to size of about 7 million light years. The horizon distance during the radiation-dominated era is 2 CT, as we said, and if I plug in 55,000 years, I find that the horizon radius is about 110,000 light years. This means that from a given point in the universe, you can see all the way to 110,000 light years away back to the Big Bang. This is interesting because it means that your causal past, all the things that could have influenced you, is a ball of radius 110,000 light years around you, which makes it kind of strange that a ball at that time of radius 7 million light years, which is what we now perceive as the surface of last scattering, could have a temperature uniform to within one part of 100,000 when different pieces of that sphere had not yet been able to communicate, and in fact have not communicated yet. We will have to discuss this. The constancy of T, despite the fact over distances much larger than the particle horizon, is something that we will have to discuss. Now, as I said, as you go farther into the past, we start at the temperature of about 17,000 Kelvin at the radiation matter transition, and as we move into the past, temperatures increase, and as they increase, more and more particles become relativistic. You recall our table. This is an opportunity to correct the pion row. This is the correct row that should have appeared in the table a while ago, and we see here, for example, that at a temperature of about 5 billion Kelvin, kBt is of the order of the mass of an electron. But I asserted earlier that electrons fall out of equilibrium at about twice that temperature. Let's understand why that happens. This is will introduce a theme that we might meet later on. At about, I claim, kBt of 1 MeV, this is about 10 to the 10 Kelvin, and this is the last time I'll make that translation probably. And this is a few seconds after the Big Bang. So we've jumped from 55,000 years back to a few seconds because all of the interesting things in the radiation era happen at its very beginning. This is when the average energy of the energy of an average photon is about twice the mass of the electron. As the universe expands and temperatures drop below this, photons can no longer pair produce. So the reaction where a photon interacting with some matter decays into electron-positron pair with a total mass of twice the mass of the electron, or a total rest energy twice the mass of the electron times c squared. So I should say this is MEc squared. I've fallen into old particle physicist habits of setting c equal to 1. When a photon is no longer able to pair produce, electrons, if they meet a positron, are still able to annihilate. An electron and a positron produce two gammas. Now, what this means, at that time, neutrinos have already decoupled. How do neutrinos decouple? Well, neutrinos certainly don't have a problem. There's no energy limitation on producing neutrinos. They are massless. However, the reactions that produce neutrinos are the weak interaction. The relevant particles are protons, neutrons, and electrons. And the interactions, cross-sections, are sufficiently small, the interactions are sufficiently rare, that by about this time in the history of the universe, a neutrino can travel all the way across one horizon distance between successive interactions, so effectively neutrinos no longer interact. The universe expands so fast that neutrinos fall out of thermal equilibrium. Energy is no longer exchanged effectively between the rest of matter and neutrino. Now, given that, the absence of effective neutrinos and no photon annihilation, there are no processes that produce electron-positron pairs. What that means is that as electrons and positrons annihilate, their numbers are not replenished. And so despite the fact that the energy is above the mass of the electron, times c squared, I correct myself, despite this, the numbers of electrons and positrons fall out of equilibrium. Essentially, at 10 to the 10 Kelvin, electrons and positrons stop being part of the radiation field, and as they annihilate into photons, they are injecting energy into the photon field. This raises the temperatures of photons precisely as G is declining. An electron and a positron each contribute two potential polarizations times some factor for being fermions of perhaps 7/8 to this number G star. And so G star is decreasing. I said the temperature rises. The way it rises is that the pairs of electrons and positrons that annihilate are injecting energy into the photon field. Because they're not injecting into the neutron field, neutron temperatures are a factor of the square root of 3 lower than the cosmic microwave background temperature. As I said, there is a cosmic neutrino background. It has not been detected because detecting neutrons is a lot harder than detecting photons. Now, what this means is all electrons and positrons annihilate. In a short time, there are very few positrons left. In our universe, we have very good evidence to show that there are no concentrations of positrons. If there had been equal numbers of electrons and positrons, they would all have annihilated. There would not be any electrons left either. But as we know, there are quite a few electrons left in our universe. Enough electrons to make all of the hydrogen atoms that make up the universe. This means that initially there were more electrons than positrons. Why and how that happened, that there are more electrons than positrons, is something we'll have to go back to. This is a problem called leptogenesis, and it is another issue we note, set aside, and we'll come back to address. As you go farther back into the universe, before, when KBT was higher than an MeV, the energy in the universe was shared between photons, roughly equally, and electrons and positrons, actually 2 to 1, because electrons and positrons have more degrees of freedom. So there was twice as much energy, there's about as much energy in electrons as in positrons as in photons, each contributing G equals to 2. If you move farther into the past, then muons become relativistic, and they contribute. And remember that a relativistic particle should be thought of as at another degree of freedom, kind of like the velocity of a particle. So under thermal conditions, energy is distributed equally among all degrees of freedom. We discussed the G sigma t to the 4th over C construction of the energy density. So each of these contributes equally, and as you move farther into the past, there's more and more relativistic species. So we should go ahead, you'd think, and talk about relativistic protons. And we don't get to relativistic protons. Two other interesting events intervene as you move farther into the past of the universe. And as I said, particle physics comes into play. We were at KBT of about 1 million electron volts and a time of a few seconds. Go to KBT of 200 million electron volts. This corresponds to a time of about a few hundred thousandths of a second. And at that energy, it turns out, hadrons, protons, neutrons, pions, mesons of all kind, not the leptons, fall apart. It turns out that, we know in our current understanding of the Standard Model, protons and pions are made out of more fundamental particles called quarks. At low energy, these quarks are confined. You never find a quark or an anti-quark moving around the universe. They are not the degrees of freedom in terms of which we describe the physics we see. They are confined and bound inside nucleons or heavier hadrons, or inside mesons like the pion. But at high energies, it is a weird property of the strong force that binds the quarks inside a nucleus, an interaction called quantum chromodynamics, that at high energies, these quarks are more and more weakly coupled. And at energies above 200 MeV, a better description of the universe is in terms of essentially free-floating quarks. They no longer spend their time bound in a proton. They basically are free-floating quarks coupled to the force carriers of the strong interaction. In analogy with the photon that carries electromagnetism, these are called gluons. And because the gluons are colored, much like the graviton carries energy, the interaction is nonlinear and complicated, and creates something possibly that we call a phase of matter that we call quark-gluon plasma. This is of interest in understanding the Big Bang and in understanding the structure of nuclei, which is why the rather impressive-looking star detector in this image on the right is attempting to create the conditions similar to those that existed during the quark-gluon era by smashing heavy nuclei, say gold nuclei, into each other at relativistic velocities, and for a short time creating temperatures and densities approaching those that we are talking about. So at this energy, at a few hundred thousandths of a second after the Big Bang, we have a transition from the quark-gluon plasma where this congeals into nucleons, and for the first time we have protons, pions, electrons, etc. By this time, the protons are no longer relativistic, although the pions are. At a higher energy yet, at 100 billion electron volts, so this is a time corresponding to about 10 to the minus 11 seconds after the Big Bang. We are crowding back to the beginning. There's another phase transition, this time associated to the weak interaction at energies above 100 GeV. The correct description of the weak nuclear force unifies it with the electromagnetic forces into something called the electroweak interaction. This transition is characterized by, as you move forward in time, as the universe cools past 100 GeV, the famous Higgs field that permeates space congeals down and settles to its non-zero expectation value that we measure. Electrons and muons and so on are now massive. Before that, they were best described as massless particles. Of course, the masses that they obtain are irrelevant compared to their thermal energy, so this doesn't change very much. But later, as the universe cools, the fact that they have a mass through this interaction with the Higgs field becomes crucial. I should point out that this Higgs field that permeates the universe, as far as we know, contributes zero energy. It is a vacuum state. If it has some finite energy density, then that would be part of the cosmological constant. We might discuss that later on. But this is not a density of massive particles, massive Higgs particles associated to the Higgs field. Is a Higgs particle, and the Higgs particle is a very massive particle that only recently has been produced in our accelerators and detected, and that was the famous discovery a few years back. Space is not permeated by a density of Higgs particles. As soon as the transition occurs, the Higgs particle is by that time about to decouple from the relativistic. It's pretty much non-relativistic. Its mass is on the order of 115 or 120 GeV, and so it's barely relativistic at the transition, and very soon thereafter, most of the Higgses annihilate, and the universe is not permeated with a cosmic Higgs background, although it is permeated by the Higgs field, which is something different. Important distinction. Can we push even earlier to the beginning? Well, earlier to the beginning involves higher temperatures, and higher temperatures involves higher energies. In fact, higher energies than we have produced at our accelerators. And so our theories that describe the behavior of matter at yet higher energies become increasingly speculative because untested. And so at higher temperatures, we are making guesses. A popular guess is that at kBt of the order of 10 to the 15 GeV, so this is, notice, a huge jump from 100 GeV to 10 to the 15 GeV by 13 orders of magnitude. We don't expect that much to happen in between these, but it's hard for me to explain why, and we might be wrong. There is expected to be another sort of symmetry-breaking transition along the same lines as the electroweak transition. This has to do with grand unified theories in which not only the already unified electroweak interactions are merged in some unified version together with the strong nuclear force. This is expected to be accompanied by another symmetry called supersymmetry, which is another conjectured theoretical symmetry of the world. We won't have time to discuss supersymmetry, but I can give you some of the evidence that suggests that there is a grand unified supersymmetric theory at about 10 to the 15 GeV. Remember, I told you that as you go measure the strong interaction at higher and higher energies, the effective interaction becomes weaker. The strong interaction is, of course, much stronger than electromagnetism or the weak interaction, and therefore saying that they are all part of the same interaction sounds weird. If they were all part of the same interaction, they would have the same strength. However, their coupling strength depends on energy. And so what is plotted here, energy is increasing to the right, and coupling strength, for bizarre reasons, is increasing down. What we see is that as you go to higher and higher energies, this yellow line indicating the strong interaction moves up. The effective strong force coupling decreases. The purple line is the weak interaction. It too has this nonlinear feature that makes the effective interaction strength decrease, but not so much. And in fact, the strength of the electromagnetic interaction increases with energy. It does not have that nonlinear property. But if these are all aspects of one unifying interaction, then all of these coupling constants should meet. These three lines should meet, and when you look at it, you notice that they do not. However, if you make the modifications to the theoretical, this is a theoretical prediction, of course, none of this has been measured. Our experiments take place way down here. But if you make modify the theoretical calculation by introducing the additional degrees of freedom of something called not the standard model of particle physics, but the minimal supersymmetric standard model, so a supersymmetric version of the same, you notice that now, not because that's how you designed it, but now these three lines meet to within the errors at which we can predict them, and they meet at an energy of the order of 10 to the 15 GeV. This is the reason that we expect grand unification to set in at energies of 10 to the 15 GeV, but as I said, this is speculative. So we don't really know much about the physics at these high energies, but we do know at least something that we do not know. What we know is that whatever theory describes physics up to energies of about 10 to the 19 GeV, and here I remember this is about 10 to the minus 44 seconds after the Big Bang, farther back we cannot go. This temperature corresponds to an energy called the Planck energy. If you divide it by c squared, you get something called the Planck mass. It's a quantity with the dimensions of mass formed from the fundamental constants of nature, Newton's constant, Planck's constant, and the speed of light. As you see here, it's about the mass of on the order of 1 billion protons, and at this energy scale, quantum gravitational effects become important. Well, so we should use our theory of quantum gravity, but we don't have a theory of quantum gravity, and so discussing even at any speculative level the behavior of the universe before what's called the Planck time, the time at which this was the effective energy density, is beyond the realm of the current tools of theory, and some fools like me are working on trying to address this. But for now, since all the way back to certainly on the order of 10 to the minus 30 seconds when KBT was 10 to the 15 GeV, we pretty much have the theoretical tools to understand what the universe was doing. Notice that we have not yet found those primordial fluctuations, and we have a few questions that we will try to address, and we'll turn to that soon.